Welcome students. Now we are going to a new topic, energy stored in a capacitor. We are going to derive the expression for the energy stored in a capacitor. Before going to that, let me ask you one thing. How you are going to charge a capacitor? You have to give charges to the capacitor, then only it will be charged. That means, suppose this is a capacitor, a parallel plate capacitor having two terminals. This is plate A and plate B. If you want to charge it, you have to give the charges to these two plates. How you will give? You just connect a battery. Connect a battery like this. This will get charged. So what happens? The positive charge will move to this point, and what happens as the positive charge moves to this plate A, there will be the movement of positive charge from the terminal this point, and there will be a movement of positive charge from this plate. So what happens? This will become negatively charged. Actually what battery is doing is, it is taking positive, imagine like that, actually it is electrons taken from here to here, but let us think like this. Here the positive charges are taken from this plate, and by doing some work by the battery, it is transferred to here. So both the plates will get equally charged. Thus the capacitor is getting charged. Here who is doing the work? The work is done by the battery. So that work done is stored by the capacitor. So in the end of the video we will find that the charge of a capacitor, the charge stored in a capacitor will be equal to half into Q into V. Half QV. Okay. That is, if Q charges is passed through this battery, if Q charges pass through the battery, the energy stored will be equal to half Q into V. Who did the work? This battery has done the work. And what is the work done by the battery if moving Q charges? If the potential difference is V, what is the potential difference? Potential difference here it is V. And that will be the potential difference between these two. Same thing. So potential difference means it is the work done in bringing unit charge from one point to another. So bringing one unit positive charge from here to here, battery has done a work of V. For Q charges, how much work will be done? Work done by the battery will be Q into V. And what that energy is stored in the capacitance, and we will show that the capacitance, the energy stored in the capacitance is half into Q into V. Energy spent by the battery is Q into V, but the energy stored in the capacitor is only half of that. Where the half has gone? Energy spent by the battery is Q into V, and the energy stored in the capacitor, that we are going to prove, that is only half into Q into V, where the other half has gone. And that is in this video. You see the video till end. Okay, friends, now we are going to study energy stored in a capacitor. How much energy is stored in a capacitor? Suppose, imagine these are two parallel plate capacitor. It's a parallel plate capacitor having two plates. Now imagine that you are connecting the terminals of the capacitor to a battery of potential V. What will happen? The charge will move to this one, and this plate will get positively charged, and the charge is coming from the battery, and at the end this positive charge will be taken from this plate, and this plate will become negative, or in other words you can say by induction it has become negative, electrostatic induction. See, actually what happens is from this plate positive charge is taken and deposited in this plate. That is done by the battery. Now let us see what is the energy stored in it. So initially you think at the moment when we are connecting, this plate is not charged. The moment I connect it to the battery, imagine that one charge flows. Whether a battery has to do any work? No. Because here there is no repulsive force. There is no force and nothing is repelling this positive charge. Now battery is sending the second charge. So there will be a small repulsive force by the first positive charge. Now it is sending the another positive charge. So there will be little more repulsive force. Like that. So as the charge of this increases, what happens is the repulsive force increases. In other words, the potential of the plate is increasing. So during the charge, initial first charge, the battery is not doing the work. In the last charge, when the battery transfers the last charge, the battery is doing the maximum work. Understood? So this work done is stored as energy in the capacitor. So let us see how the work is done. Here you cannot simply find out the potential and multiply Q into V. Like that you cannot, because the work done in the last, bringing the last charge is maximum, and work done by the battery in bringing the first charge is minimum. So you have to do some integration. So at any instant of time, suppose imagine that it is filled with 1 lakh charges. So what I am saying is at any instant, suppose the charge is 20,000. At that instant, it is charging 1, 2, 3, 4. Imagine that 1 lakh charges has accumulated here. 1 lakh here also, because charge is transferred from here to here through this way by the battery. So imagine that a total charge is 1 lakh. I am considering the case where the charge is 20,000. So in between, somewhere in between I am saying, let charge be Q at that instant, at any instant. Let Q be the charge in the capacitor. So if there are Q charges, then there will be a potential difference between the plates. There will be a potential. Let V be the potential at that instant. So at a particular instant, the process of charges is going on. At a particular instant, I am imagining that Q is the charge in it and V is the potential. Okay. Now, at that moment, I am transferring a small charge dq from here to here. Here to here means actually the charge is transferred from here to here, plus dq from here to here, plus dq. Q is the charge. Now I am adding a small charge dq. Okay. So actually it is equivalent to transferring the charge from here to here, because electrostatic force, the work done by the battery is against the electrostatic force between the plates. So electrostatic force is a conservative force. That means if you bring one charge from one point to other in this way or that way, this way, the work done will be the same. So that means if actually you are bringing charge this way, and that is equivalent to bringing charge this way, so the work done will be the same. Now imagine the potential difference between the plates at this instant is V. Then what will be the work done in bringing plus dq charge from here to here through this path, but I am considering only from here to here. What will be the work done? V is the potential. What is the potential? Potential is the work done in bringing unit charge. So what will be the work done in bringing dq charge? So the work done dw will be equal to dq into V. This is the work done in bringing a small charge dq. Now what you have to do in order to find the work as energy stored in it, this work done is stored as energy. This dw work is stored as the energy in this capacitor. So in order to find out the total work done, that will give you total energy. What you have to do? You have to consider all the dw's. You have to calculate all the dw's from zero charge to maximum charge. Let it be Q, capital Q. So from that point you have to work out all the dw's and get added. That means that is called integration. So total work done, and that will be equal to energy stored. This is work done. Total work done. Who is doing that work? Battery. Total work done will be equal to energy stored, and that will be equal to integral dw. That means you have to add it all the dw's together. So, but dw is equal to dq into v. So I can write energy stored is equal to integral v dq. Here V is the potential and dq is the charge. You cannot integrate these two. Either you have to convert V in terms of dq, or you have to convert dq in terms of V. Both you can select. So I will show both. So this is equation number 1. Now I am converting in terms of V. Here it is V and here it is dq. You cannot integrate like that. So what you have to do? You have to convert either V in terms of Q or dq in terms of V. Now if we are bringing dq here, dq charge here, what will be the rise of potential? The potential will get raised. Actually it was V. When dq charge comes, the potential rises by dV. Okay. So I can write energy stored is equal to integral of V. Instead of dq, I want to write it in terms of V. Suppose C is the capacitance. Then what is the relation between C, Q and V? Q is equal to CV. So what will be dq? dq will be equal to C into dV. C is a constant. That is for a particular this parallel plate capacitance, C is a constant. So I can write dq as C dV. And what is the limit of integration? Limit of integration is from 0 to capital. Say at the final stage, that the potential be V0. The potential at the battery is V0. Imagine that. I have taken V in between that. V is the potential when 20,000 charges are introduced. When the 1 lakh charges are introduced, it will come to V0. So I have to integrate from 0 to V0. Or since C is a constant, you can take it out. C into integral 0 to V0 C V dV. And what is integral of V dV? It is V square by 2. So this will become C into V square by 2 limit 0 to V and V0, and that will be equal to half C V0 square. So in general we can write the energy stored in a capacitor is stored in a capacitor U is equal to half CV square. This is one expression. Okay. Using this Q is equal to C into V, by substituting the value of V, instead of V we can write Q by C, you will get another expression. Before that I will come to one more point. This is the expression you got. Equation number 1. Earlier I told that you can convert V in terms of Q. What will be V? V will be equal to Q by C. So you can write here integral, instead of V I can write Q by C dq. Then what will be the limit will be 0 to Q0. Q0 is the maximum charge given by this battery. So you can write like this also. So this will be equal to 1 by C into, C is a constant that I am taking outside. So Q dq. And that will be equal to 0 to Q0. And that will be equal to 1 by C into 1 by C into, that will be equal to 1 by C into, what is Q dq? Integral dq dq is Q square by 2, 0 to Q0, and that will be equal to 1 by C into Q0 square by 2. Like that. Now we can write U is equal to, energy stored in a capacitor will be equal to half into Q0 square by C. This is another formula. This you can write U is equal to half into Q into V. Suppose what is C? C is equal to Q by V. So you can write Q square by C is equal to Q by V. So Q square by, instead of C I am writing Q by V. Q by V. So Q and Q will cancel. U is equal to half QV. This is another formula for energy stored in a capacitor. So energy stored in a capacitor is either half CV square or half Q square by C or half Q into V. This is the energy stored in a capacitor. Now let us see what is the energy given by the energy spent by the battery. Energy, see, the battery has taken Q charges, Q0 charges from here to here, or in general Q charges from here to here. Okay. So what will be the work done? The potential is V. We will take it as V. We will avoid that V0. The potential is V. So what will be the work done? Work done will be equal to, it is the work done in bringing unit charge. It has brought Q charges from here to here. So what will be the work done? Work done by the battery. Work done by the battery it will be equal to Q into V. So this is the energy spent by the battery, and this is the energy stored by the capacitor, where that half of its energy gone. That energy is spent for, that will be released at heat in this conductor, as well as there is an internal resistance in the battery. Every battery that you are going to study in current electricity, every battery is having, every cell is having an internal resistance. Without internal resistance you cannot create a battery. Okay, so that energy will be gone within the battery itself. The battery itself get charged, itself get heated. So that energy will be lost as heat, and the battery will get little more heated. So half of the energy will be lost by heat in the internal resistance of the battery, and this conductors, wires, that also will get slightly heated. So the half of the energy will be lost in between these conductors as well as the internal resistance. Without internal resistance you cannot create a battery. And if you use, in order to avoid the heat loss or the resistance due to this one, even if you use big wires, energy will be lost in the internal resistance of the battery. Okay, that is why the energy is reduced to half of it. Okay, please note down.